coming at you.
Here's something to set the mood. We're going to talk about a little water and sewage and solid waste. But your textbook, your Civil Engineering Reference Manual, starts off the topic with water chemistry. Water chemistry is, some people call water chemistry the chemistry of dilute solutions. In the water chemistry that is outlined in your book and that I'll cover tonight very briefly, we assume that the density of the solution is 1 for most waters and for wastewaters, with the exception of seawater and brines. There's 2 basic ways that you could express concentrations of solids, of dissolved solutes in a solution. You can talk about the weight of a solute and in a volume, or you can talk about the weight per weight. The weight per unit volume would be milligrams per liter, and weight per weight is parts per million. Generally speaking, most liquid problems that we have in water and sewage, we weigh the solids in the laboratory, and then we may add those solids to a known volume, to a total volume. We use a volumetric flask, so we would weigh out a known amount of solute, and we would add it to a fixed volume. We'd add it to a volume and make it up to a certain mark. Most sludges, though, we end up weighing the solids and then we might express those in parts per million. But actually, parts per million and milligrams per liter are equivalent as long as you have dilute solutions and as long as you make the assumption that the density of the solution is 1, and we make that assumption for most of the problems, and it works out. Now, there's another thing that we normally do in this water chemistry, and you know, the people that work at water treatment plants and sewage treatment plants, for the most part, in the beginning, were not college graduates, but they had to learn this chemistry, and so they found some ways to work these chemistry problems without learning a lot of fundamental chemistry. So what they tend to do is to express concentrations of things in terms of something else. You might express alkalinity in terms of calcium carbonate. So you may be thinking about hydroxide ions, but you express them in terms of calcium carbonate. We express nitrogen, nitrate, for example, in terms of nitrogen. We may express phosphorus in terms of phosphate. So you have to be a little careful about how this works out. You've got to know how the concentrations are expressed in what terms, and for this makes sense. Now, if you look at your handout, they were stacked in order, and I assume they're still in that order. So the first sheet should be BC1.
That's right.
And I'm going to slide over so you can say BC1, and that's a set. And the next set is CL, and we'll take them in sequence. But then the next set is WT1, and then there's one called water filtration, and then there's one called potable water, and then there's a set called SET for settling, and then finally there's one that's called it's not called anything. It's Xerox copies out of your Civil Engineering Reference Manual, out of Chapter 7. And I'm going to start in a few minutes with one of the pages in that Chapter 7. If you go to page 716, I'll project that. We're just going to look at it for a few minutes. On page 716 of that page, there's a table that shows Table 7.9. Typical water quality standards. And if you look down the line there's nitrate. It says typical water quality standards, the minimum or the maximum concentration level for nitrate is 10 milligrams per liter. Well, what does that mean? 10 milligrams per liter of what? Nitrate is NO3, as you probably recall, and nitrogen is N. And nitrogen has a valence of has a potential valence of it has 1, 2, 3, 4, 5, 6 valence states, and so it could have a valence of -3, +1, +2, +3, +4, or +5, and nitrate is NO3. So if they mean nitrate as nitrate, then 10 milligrams per liter would limit the nitrogen in the nitrate to 2.26 milligrams per liter. But in this particular case, you just have to know or read that when they say the nitrate is limited to 10 milligrams per liter, they mean the nitrogen in nitrate is limited to 10 milligrams per liter. You'd measure nitrate, but you would express the results in terms of just the nitrogen. So you could have 10 milligrams per liter of nitrogen in the form of nitrate, and that would make a difference. You just have to be aware of that, and be sure you in your computations read the concentrations properly. Okay, now then let's go on with the discussion here. I want to start with example 1.1, and it's a nice simple example. Let me zoom out on it.
What page is that?
And it's the first page, DC1.
Okay.
And it says find the normality of the following solutions. And they give two solutions. And they want to find the normality of 60 milligrams of a carbonate per liter, given that carbonate participates in the precipitation reaction. I'm trouble with participate in precipitation in the same sentence reaction. So you have calcium plus carbonate yields calcium carbonate. And so let's look at that one first. The solution is down below, and it's the molecular weight of carbonate is 60. Carbon is 12. Oxygen is 16. There's 3 oxygen, so 3 times 16 is 48. Plus the 12 gives you a total of 60. So the molecular weight is 60. The gram equivalent weight is the gram molecular weight divided by the ion charge. That carbonate has an ion charge of 2, -2. You see it says CO3 with a 2 minus. That means it's got a valence of -2. And so you divide 2 into 60 and you get 30 grams per equivalent, or 30 milligrams per milliequivalent. There's 1,000 milligrams in a gram, and there's 1,000 milliequivalents in an equivalent. So they just 30 grams per equivalent or 30 milligrams per milliequivalent. So the normality is, since you started with 60 milligrams per liter, you divide the 60 by 30. See, we started with 60, so we divide the 60 by 30 and cancel out the units there, and you get 2 milliequivalents per liter. The second problem is 155 grams of calcium phosphate, and it gives you the reaction. And so from that reaction, then because each calcium phosphate forms 6 positive and 6 negative charges, then in this case you got to calculate the molecular weight is 310. You take 3 calciums, 2 phosphorus, and 8 oxygens. You get 310, and divide it by 6 equivalents per mole, and you'd come up then with 51.67 milligrams per milliequivalent. And the normality then would be 155. You start with 155, divided by 51.67, get 3 milliequivalents per liter. The next page, just going right down the line, is example 1.2. Which you got in front of you. And it says find the normality of the following solutions, and the first solution is 36.5 milligrams of hydrochloric acid with respect to the reaction, and then they give you the reaction. And so you're going to react hydrochloric acid with sodium hydroxide. And so 1 hydrogen reacts per mole of hydrochloric acid. Therefore, we find the gram equivalent weight is the gram molecular weight, which is 36.5. That's the molecular weight of chlorine, which is 35.5, plus hydrogen, which is 1. And follow through. I don't know that we really need to work all of these. What you have to do is you have to know the reaction that you're looking at to get the normality. Normally, in the laboratory, you set up solutions to measure various things, and so you'll set up the solution, the laboratory, at a normality that's convenient to you, so that each milliliter might result in 1 part per million. Each milliliter might result in 1 milligram per liter. In order to calculate this, you have to come up and express the concentration of these materials, not so much in terms of milligrams per liter, but in terms of the normality, in terms of the moles per liter or milliequivalents per liter. I want to go to example 2.5. On page 3 is an example, but you can just follow through. But on page BC4, there's example 2.5. And it says tests for common ions are run on a sample of water, and the results are shown below. If a 10% error in the balance is acceptable, should the analysis be considered complete? So they ran calcium, magnesium, and sodium, and they ran sulfate, chloride, and bicarbonate, and so they add up the positive ions and the negative ions. But in order to add these up, they changed them from milligrams per liter to the equivalent concentration, milliequivalents per liter. In this particular case, we'll go back and see how they calculate them. In this particular case, let's answer the question. The cations added up to 8.49, and the anions added up to 7.86. The percent error there is 8.49 minus 7.86 divided by 7.86 times 100 is 8%. They gave you a 10% error, so the analysis is good. And then down below, they show a graph showing the milliequivalents, and it's just the cumulative sum. They start with calcium, which was 2.75. Then they went to magnesium, 2.75 of calcium, plus 1.48 of magnesium, ended up with a total of 4.23. This is the cumulative sum, and then finally 8.49. And down below, they plotted the same thing for the anions. And this is a way to see if you've left something significant out. Now, if you've left 2 significant things out, I guess drawing this sketch wouldn't help find it. Let me I'll go back to that the bicarbonate. Looking at the bicarbonate, looking at the calcium. Look at the calcium over here. The atomic weight is 40. The concentration is 55. The valence is 2. So the equivalence, milligrams per milliequivalent, is 40 divided by 2. And you divide the 55, divide the concentration 55 by 40 divided by 2. So you divide 55 by 20. And you get 2.75. On the case of in the case of the bicarbonate, you had 250 milligrams per liter, and the valence is 1, and the weight is 61, and so you divide 250 by 61, and you get 410 for the equivalent concentration. You see how that's done? Any questions before we go to the next page?
No.
Okay. Example 2.6 on page BC5, determining total alkalinity. Now, your book has a nifty way of working alkalinity. I really like it. I like the technique. I also like this technique, and it's just entirely different. It's also convenient. So I picked out this problem because sometimes I think these alkalinity problems can be difficult, and I don't work them often enough. So when I work them, I have to follow a pretty good set of instructions. And so in this case, you got a 200 milliliter sample of water. This is example 2.6 on BC5. You got a 200 milliliter sample of water, has an initial pH of 10, and you would measure that in the laboratory. So you measure the pH is 10, and you would record that. And then you added, it took 30 milliliters of a 200's normal solution of sulfuric acid to titrate the sample to a pH of 4.5. And you could either use an indicator to tell you you're at a pH of 4.5, or you could use a pH meter. Presumably, since you measured pH, you could use the pH meter. And what is the total alkalinity of the water in milligrams per liter as calcium carbonate? Well, he said because each milligram of the 200th normal solution of sulfuric acid will neutralize 1 milligram of alkalinity, then there is 30 milligrams of alkalinity in the 200 milliliter sample. Therefore, the concentration of alkalinity is 30 divided by 200. You ought to express it in milligrams per liter, so you'd multiply by 1,000. There's 1,000 milliliters in a liter, and you'd come up with 150 milligrams per liter. And then he's got a little discussion down below, which I think is handy, and I will go through it quickly. But I think you need to sit down, and I would suggest if you're going to try to work up some skill at working these problems, you practice working some of these problems, and try the technique in the book. The one in the book is a graphical solution. He goes through a flow chart. This one, you have a set of rules, and you could, of course, set up a flow chart. But if the volume of acid needed to reach the 8.3 endpoint is known, the species of alkalinity can also be determined. And so what I thought I would do is let's look at the next page, which is an example problem. We'll be flipping back and forth between BC5 and BC6. Now, I won't flip back and forth. I'll try to stay focused on page BC6, but I will tell you to refer back. You got that page. And so this example, he says, determine the alkalinity species. Determine the species and the quantity of each species of alkalinity if the 8.3 equivalence point is reached at 11 milliliters of acid. And so if you look at the previous page, he defined P and M. And P is the amount of acid required to reach pH 8.3, and that was 11. And M is the amount of acid that it takes to reach a pH of 4.5. And this problem, that's 30. So you know P is 11 and M is 30. And then you can go back and you can follow the rules. If P is equal to M, all the alkalinity is OH. Well, is P equal to M? No, it's not. So go to the next one. P is equal to M over M divided by 2. Dividing M by 2 is 15, so P is not equal to M over 2, so go to the next rule. P is equal to 0. Well, that's not true, so go to the next rule. P is greater than M over 2. And that's not true, is it? And then P is less than M over 2. M over 2 is 15 and P is 11, so it's that last rule, right? P is greater. I'm sorry, I misread that. The last one is P is greater than M over 2. So actually what we have is P is less than M over 2. Is that right? It'd be the next to last rule?
Right.
Okay. So P is less than M over 2. Predominant species are CO3 and HCO3. Okay. But he has sometimes that's all you need to know. You just need to know what the dominant is. If you want to know the actual amounts, there's a solution on page B6, but he uses those rules. Solution number one, because the initial pH is 10, the initial pOH is 4. You know where that comes from, right? The total is 14. You got pH 10, 10 from 14 is 4, okay? So a determination of the OH concentration can be made. It's 10 to the minus 4 moles per liter of hydroxide times 1 equivalent mole times 50,000. They're converting it to calcium carbonate, and you can work this out by adding up the calcium and by adding up the carbonate. I think it's one of the examples that I skipped over, and so you end up with 5 milligrams per liter as calcium carbonate. Now it says 5 milliliters of acid would be required to measure the OH in the 1 liter sample. However, this sample is only 200 milliliters, so the necessary volume of acid is, again, 5 times 200 divided by 1,000, which is equal to 1 milligram per liter. Because we only had 200, it would take 5 milliliters if we'd had a liter sample. In this case, we've got a 200 liter sample, so it takes 1/5 of that. And then he says if 1 milliliter of acid measures the OH, then 10 milliliters of acid measures 1/2 of the carbonate, and 10 more will be required to measure the remaining 1/2, leaving 9 to measure the bicarbonate. And you don't need to see figure 2.4. What you need is to go back to page BC5, those rules, and so you can work it out. And so from this simple titration, then you can find all the species of alkalinity. The next problem is skip page B7 and go to page B8, and problem 11.2. Water contains 50 milligrams per liter of calcium ion and 15 milligrams per liter of magnesium ion. Express the hardness as milligrams per liter of calcium carbonate. And then B is alkalinity in the water consists of 100. Well, let's skip number B and let's just work the first part. A. We want to know the total hardness. Well, the total hardness is the calcium plus the magnesium. Hardness is the divalent or trivalent ions, metallic ions, positive ions. So in this case, we got 50 milligrams per liter of calcium and we got 15 milligrams per liter of magnesium. We want to add those up, but we're going to add those up in terms of calcium carbonate. Well, the molecular weight of calcium carbonate, you got 1 calcium, 1 carbon, and 3 oxygens, is 100. And since we're dealing with things with a valence of 2, then dividing 100 by 2 gives us 50. So that's the total hardness is equal to 50. That first 50 is the 50 milligrams per liter of calcium that we have. This second 50 is 100 divided by 2, the molecular weight of calcium carbonate divided by a valence of 2, and the 20 is the molecular weight of the calcium divided by 2. And it's plus 15. That 15 is the 15 milligrams per liter of magnesium. This 50 is still the calcium carbonate, and this is half since the valence of magnesium is 2, that's half the molecular weight of magnesium. So you end up with 186 milligrams per liter expressed as calcium carbonate. So in this case, you've got some calcium and you got some magnesium. Expressing those in terms of calcium carbonate, you have 186 milligrams per liter. The total alkalinity, you got the 150 milligrams per liter and you got 150 one species, 15 of another, so you got to add those up. And again, this 150 is the concentration that's given. This 15 is the concentration that's given here. This 50 is 1/2 the molecular weight of calcium carbonate. This 61 is 1/2 the molecular weight of a bicarbonate ion, and this is the bicarbonate ion. Okay. The next problem on the same page. Any questions before we're going? I'm going through these kind of fast because we have to cover all that. The next problem is they want to draw another a leader bar graph for the analysis of salt water. They got 36 milligrams per liter of calcium and 14 milligrams per liter of magnesium, and so on. You can read those. And so they set up a table. So you list all of the elements, all the molecules there that you've analyzed for, and you write down the concentration in milligrams per liter, and then you come up with the equivalent weight. For calcium, the molecular weight is 40, valence is 2, so 40 divided by 2 gives you 20 for the equivalent weight, and then you divide 20 into 36. Divide the 20 into 36, you get 1.8 milliequivalents per liter. Let's skip down to this one. This has a molecular weight of 61, valence of 1, so that would be 61. 61 divided by 1 is 61. Divide 61 to 208 and you get 3.41. And then you can draw the chart. Any questions about that? Okay, on page BC9, there's a problem 11.4, and it's just more of the same thing. I believe we'll just skip that one. And then that concludes this first section. So now the second group, second set is labeled chlorine, Cl. And I'm going to look at CL, page CL1, but I'm going to do it last. I numbered these. I changed my ideas about how to present this. So I want to start out now with CL2. CL2 looks something like this. I'm not going to read all that to you, but you'll notice some similarities between what's on page CL2 and what's on page CL1. But I'll point this out to you when I come back to CL1. But CL2, that page, just talks about chlorination, and I would suggest that you read that along with the information that's in your book. I think this gives it a slightly different viewpoint. It gives you same information, but slightly different presentation. And so when you take chlorine gas and you add it to water, you get hypochlorous acid and you get hydrochloric acid. This is the hypochlorous acid, the HOCl. The HCl is the hydrochloric acid. Chlorine, the chlorine gas Cl2, is what's called, and it can actually be in solution in the water as a chlorine gas under the right conditions, under the right pH conditions. And if it occurs, that's free chlorine. The HOCl is also free chlorine. The HCl is not part of the chlorination system. It has no disinfectant power. So when you add chlorine gas, half the chlorine is used to form hydrochloric acid, which doesn't contribute anything to disinfection. Now, in dilute solutions with a pH greater than 3, the reaction goes on to the right, and you have very little chlorine gas. So most of the time when you add this water, you're not going to have any chlorine gas in solution in the water, unless the pH is less than 3. Now then, the hypochlorous acid will then dissociate to yield what they call the hypochlorite ion. That hypochlorite ion is also known as free residual chlorine. Okay, and then the relative distribution of HOCl and OCl is shown on this sketch. You notice as the pH progresses to the right, you end up with less and less HOCl, and you end up with more and more OCl. Now on page 1, I'm just going to go back to it for just a minute. There's a similar graph, but it goes to a lower pH, and it shows the chlorine gas. You notice it disappears. You start picking up HOCl, it disappears, and you start picking up the OCl. And that would be all the free residual chlorine. The free residual chlorine is not the chlorine that you add. It's the free residual chlorine is that's left after it's reacted with whatever it's going to react with in the water, other than the water. In other words, chlorine is an oxidizing agent, and so it'll oxidize organic matter and any impurities in the water. And the free residual is that's left over in the form of chlorine gas, HOCl, hypochlorous acid, or hypochlorite ion. And then equation 17.5 shows how you can buy hypochlorite salts. In this case, it's calcium hypochlorite. You can buy this powder, and you can use it. You'd use that for small plants or for emergency situations. Sometimes in hurricane zones, people will fill up their water towers before the hurricane hits to get it heavy, get it full of water, and they'll shut it off in case houses blow away and they destroy the water system. At least they got a tank full of water, and it should be clean water. But you can chlorinate it by climbing up there and dumping some powder in it if you need to. Let's go to page CL3. And he shows the reactions with ammonia. Let me zoom in on this some. There's the reactions with ammonia. Now this ammonia, the NH3Cl, the NHCl2, or the NCl3 is the combined residual chlorine. And I'm using the wrong. I have these pretty blue ones, and I'm not using those. Can you tell a big difference between that? Bet you could. It was a different page. Between that page and this page? Does that show up better?
I think I don't know. The first one might should have been a little bit better.
Is that right? Awesome.
Either one, they're about the same anyway, so it doesn't matter.
Well, I was supposed to be showing you I put notes on my white ones, and I was supposed to be showing you the blue ones.
Oh, I see.
And,
either one.
Yeah. But anyway,
use the blue.
They told us that the blue was better, or somehow we thought it was better.
That's fine. It's close enough.
But anyway, these are monochloramine, dichloramine, trichloramines, and these are called combined residuals. And the combined residuals aren't as effective in disinfecting or killing microorganisms as the free available chlorine. And now, one of the bad things about chlorine and with some of the recent changes in the EPA regulations have to do with the formation of chloroform, bromodichloromethane, and dibromochloromethane. These things are what they call tumorigenic. They're suspected of causing tumors, and they're a result of chlorinating. Back before the 1900s, people didn't chlorinate, and lots of people died of waterborne disease. when they started chlorinating, this mortality due to waterborne disease really went down. But it turns out that adding chlorine, and people started really adding a lot of chlorine to water. And so if you got water from a river, they just started chlorinating it from the word go. When they pumped the water into the water treatment plant, they would start adding chlorine. They just kept the chlorine in there because they got a long residual. And of course, it did kill the virus and it killed the bacteria. It killed everything in it. But in the process, it formed these other compounds, these tumorigenic compounds. The EPA has put a limit of 1/10 of a milligram per liter on these things. So now you have to, if you're going to chlorinate, if you're adding chlorine and you're forming these things in excess of 1/10 of a milligram per liter, you got to change something. The obvious thing to change is to quit adding chlorine and go to some other disinfectant. And there's lots of things that you can use to disinfect water, but what we've always used in the United States is the property of chlorine to have a residual. After we clean up the water at the water treatment plant, we put it in the distribution system, and there are accidental connections made to the water system that are cross connections. You can inadvertently hook a sewer line to a water system. And if it was a small hookup into a big system, you might not notice that until people started falling dead. But if you measure the chlorine residual, if someone has hooked some contaminant in there like sewage or some organic compound, your chlorine's going to disappear. And if your chlorine disappears, then you know that something's happened. You can either add more chlorine, and if you can't add enough chlorine, if there's one area of town where the chlorine residual is 0, you suspect a cross connection or you suspect some kind of a problem. And we've really relied on that. We really like having that residual chlorine. And there's no other contaminant we've got available that leaves a residual. The only other things that might work leave a residual, but they form more of these chloroforms, more harmful compounds than the chlorine does. So what they've done is they've quit chlorinating so much. They don't chlorinate at the beginning of the process. What it takes is that chlorine has got to react with something to form this chloroform and these other compounds. And so what we do now is we treat the water and we clean it up and we get rid of the color and the turbidity and the organics and filter it and get it pretty well cleaned up, and then we add chlorine at the end. It takes a certain length of time for the chlorine to react to form this chloroform. So if you save the chlorination until the end and clean up the water first and really clean the water up, then you can continue with your chlorination. I wanted to point out to you on page 4 shows a couple of graphs, and it shows the relative effectiveness of calculator.
I got here you go. How about underneath this other
there it is. You notice there, as they talk about the log survival, you probably don't know what that means, but let's look. E. coli is a bacteria, and you notice that chloramine, and then on the right is the chlorination effects on trickling filter effluent. And you notice that the coliforms, if a -4 is killing more of them than -1, you notice that there's a lot more killing of the coliform than of the viruses. The F2 phage 2 and the colophage. And what -1 means, that's the log of the survival. And so if you thought in terms of 10%, let's say I was going to kill 10% of the organisms there. If you got a calculator, enter 0.1 in your calculator, and then take the log of that, and you end up with -1. So -1 means you've killed 10%. -2 means that it means that 10% remain. -2 means that 1% remains. -3 means that 0.001 remains. and so on down the line. That's what that log survival means. So you can work that out with your calculator, in case someone should ask about it. Down below is a sketch showing the breakpoint chlorination. And now what happens with breakpoint chlorination, if you've got some water, now let's talk about relatively clean water. Although this would work for sewage, you can breakpoint chlorinate sewage. Most people don't because it takes so much chlorine. But when you first start adding chlorine as your chlorine dosage, and this is the moles of chlorine per mole of ammonia expressed as nitrogen. You're measuring the ammonia, but you're expressing it as nitrogen. So it's the moles of Cl2 per mole of ammonia expressed as nitrogen. And this would be a straight line. This would be a 1-to-1 slope. Well, you don't get a 1-to-1 slope because there's some reactions of the chlorine with the organics, with the impurities in the water. But after a while, you're getting mostly chloramines. After a while, though, the chloramines start breaking down as you add more chlorine, and you get this breakdown of the chloramines, and you get what we call the breakpoint. You notice the demand suddenly increases, and then the demand becomes constant beyond the breakpoint, and you have predominantly free chlorine. Now, the free chlorine can be in the form of chlorine gas, hyperchlorous ion, or hyperchloride ion, depending on the pH. And then going to page CL5 is just some more verbiage that you can read in your free time. But it talks about dosages and demands and residuals, and it's there that it defines free chlorine residuals and combined. But I've already defined that for you. And now let's go back to page 1. And page 1 shows you how you can actually calculate the amount of the different types of chlorine that are there if you know the pH. He says a chlorine dose of 1 milligram per liter is Cl2, satisfactory disinfects the water. This problem shows you how to determine how much chlorine you've got there and its relative effectiveness, because it turns out that free available chlorine is about 100 times better than the combined. In this case, the HOCl is about 100 times better than the OCl, and both those are free. But the HOCl is about 100 times more effective as a disinfectant than OCl. And so from this figure down here, a pH of 7, we can find then the chlorine would have gone to 0. So you got 0 chlorine, right? This curve is at 0 at pH 7. Okay, at pH 7, though, you do have some HOCl. And it turns out that's about 0.76. You got about 76% of that chlorine is HOCl. And you got about 24% of it as OCl. And the relative disinfectiveness of HOCl is 100, OCl is 1. And so you can calculate then the relative the disinfection effectiveness is a concentration times the relative disinfection effectiveness. So it's 0.76 times 100 plus 0.24 times 1. And so you end up with 76 units per milligram per liter of chlorine. And then he's gonna disinfect some water at pH 8.5. So you go through and you do the same thing at 8.5. You've got 0 chlorine, you got 9% HOCl, and you got 91% OCL. And the relative effectiveness there is 9.9 units instead of 76. So it takes 7.7 times the dose that you applied at pH 7. Any questions? And Now let's go to the third group of papers, and the next one is called, titled WT, I believe. Yeah, WT. Has to do with alum. It's kind of hard to tell where chemistry stops and water treatment begins, because all the chemistry problems that they work have to do with water or sewage treatment. Okay, on this page on WT1, he talks about using aluminum sulfate as a coagulant. When you treat water, if you've got river water or lake water and you have some solids in suspension, they won't settle out. They're too small. Some colloidal materials or so on, and some clays and organisms, and you want to settle them out, and they won't settle out. You don't want to. You could go directly to a filter, but it clog your filter, so you want to clean it up. So you can add a little filter alum to get a little coagulation to help cause these materials to settle out. Sometimes the question comes up, they usually call this process coagulation and flocculation. What's the difference between coagulation and flocculation? And coagulation is where you add some chemical like alum to change these clay. Let's say they're clay particles. You have a negative charge, and you have these same electrical charges repulse these particles. They can't get close enough together to flocculate. So you can add a chemical that would change the electrical charge, so the particles can get close together. Flocculation is where after you add the chemicals, you mix them slowly to allow the flock to grow. So they give the chemical reactions here, and these reactions are fairly complex, but usually the way that we measure and calculate the dose is with a jar test. And so problem 1112 is a jar test, and unfortunately for me, when I cut this thing out, I didn't pay much attention to it, and they have an error in the solution, but I've corrected it. But you haven't got the correction on your sheet. So let's read the problem. He says the results from a jar test for coagulation of a turbid alkaline raw water are given in the table. And so they got jar 1 through 6. Each jar has a volume of 1,000 milliliters of water, holds 1 liter. And they put some aluminum sulfate solution in each jar. They put 1 milliliter in jar 1, and they put 6 milliliters in jar 6. And each milliliter of solution added to the jar produced a concentration of 8 milligrams per liter of aluminum sulfate. And so on the first jar you didn't get any flock. The second jar is smoky, but that's not very good. The jar 3 is fair, but that's not what you want. Jar 4 is good. That is what you want. Jar 5 is good. That's also what you want, but that's a bigger dose. So you'd use a smaller dose. And then 6 is very heavy. But sometimes very heavy flocks don't work. They don't grow properly. So what we want is 4. So jar 4 is the one. But the dosage is 4, not 2. And so it'd be 4 times 8, which would be 32 milligrams per liter. Now then, the second part of that question says the aluminum, based on the jar test, if another jar had been filled with freshly distilled water and dosed with 5 milligrams per liter of aluminum sulfate solution, what would have been the degree of flock formation? And it would be none, because of lack of alkalinity. You got to have some alkalinity for this to work. If the water doesn't have alkalinity in it, then it's not going to work. You won't go through the chemical reaction. He says C equation 1134, and you'll notice that there's some alkalinity. There's an alkalinity term there. Without that alkalinity, the reaction, the flock won't grow. So anyway, change that answer on 1112 from 2 times 8 to 4 times 8, which would make the answer 32 instead of 16. Okay? skip page 11 too, and go to WT3. And WT3, there's talking about chemistry of iron and manganese. At the top is iron and manganese removal. What happens is the iron and manganese in groundwater, for example, in groundwater, the iron and manganese, the groundwater doesn't normally have oxygen in it, and so the iron and manganese remains in solution. You pump the water out of the well and put it in the system, get a little oxygen in it, it changed valence state, and now the iron and manganese will precipitate out. The iron becomes rust, and the manganese becomes a black gooey substance, and they'll precipitate. And so if you have more than about 0.3 milligram per liter of iron and more than about 0.5 milligram per liter of manganese, you start staining the plumbing and staining everything else. You get bad taste and so on. And so you need to remove iron and manganese. There's several ways to remove it, and they cover other ways in your text. Your textbook covers chlorination. This is using potassium permanganate, which is a process that people use. The description's there, and here's two equations, 1155 and 1156. One of them showing the reaction with potassium permanganate with iron, and the other one showing potassium permanganate with magnesium. You notice that one permanganate end of the potassium permanganate removes 3 irons. It takes 2 of these to remove 3 manganese. And so there's a problem on the next page. And sorry, got out of order. On page WT4, it says untreated water contains 1.2 milligrams per liter of iron and 0.8 milligrams per liter of manganese at a pH of 7.5. Calculate the theoretical dosage of potassium permanganate required for iron and manganese oxidation. There's the solution, but if you're rusty on this, that solution doesn't mean anything to you. So what I've done, I'm going to switch. I've got the same slide, but I've written some notes on it. And you might want to write this down. There's nothing any different on here than what we've done before. Just kind of review. Iron has a valence of 2. It has a concentration of 1.2 and has an atomic weight of 55.84. The manganese has a valence of 2, atomic weight of 54.938, concentration of 0.8. The potassium permanganate 158.036, and concentration of X. We're looking for that concentration. And so looking at the iron, we've got 1.2 milligrams per liter. And if you notice the equation from the previous page, the potassium permanganate, 1 molecule of potassium permanganate would remove 3 irons. So we got 1.2 times 3 times the molecular weight of the iron is equal to X. This is the concentration of the potassium permanganate, and this is the molecular weight of the potassium permanganate. So it turns out that X is equal to 1.132. It turns out that one manganese, potassium permanganate removes 3 irons. But down here on the manganese, it takes 2 of them to remove 3 irons. So it takes 1.132 milligrams per liter of potassium permanganate, theoretically, to remove the iron. It's going to take some additional to remove the manganese. You work it out the same way. In this case, you remove 3, and it takes 2 potassium permanganates to do it. So setting up the ratio you saw for it, and you get a total of 2.66, which he called 2.7. Up here. Yeah. Now then, how did he get the 1 over 1.06, and how did he get the 1 over 0.52? The way he got that is by taking 3 times 54.938 and comparing it to 158.036. I'm sorry. In this case, 3 times 55.084 times compared to 158.036. 3 times 55 is a little more than 150, and so you divide that by this and you get 1.06. In the case of this one, it's 3 times 54.938 times 2 times 158.036, and you get the ratio of about 0.52. But that was a little quick for me. I can't see the solution like this. I can only see the solution going through the arithmetic. I would imagine you have the same problem. Okay. There's some, if you look on page WT5, there's a problem that could end up, it'd be a nice problem. I've seen some similar to it on the exam, and this is such a simple looking problem, it would just tear you up if you'd never worked on it like it before, so I decided to put it in there. Pre-sedimentation reduces the turbidity of raw water from 1,500 milligrams per liter suspended solids to 200 milligrams per liter. How many pounds of dry solids are removed per million gallons? And look at the solution. The solution is the dry solids equal to 1,500 minus 2,000. That makes sense. So he's going from 1,500 to 200 milligrams per liter, and that would be 1,300 milligrams per liter of suspended solids that he's removing. But in order to get the pounds, he multiplied by 8.34. Well, he really didn't multiply by 8.34. What we did, you recognize that there's, he wants the answer, how many pounds of dry solids are removed per million gallons. Now, I told you at the beginning that we were making the assumption that the solutes had the same density as the water. So we're we want to convert that. We want to know water weighs 8.34 pounds per gallon. If I took 1,000,000 gallons and divided it by 8.34, I'd get the number of gallons of water. And what he wanted was this the amount of solids removed per million gallons, and that's where the 8.34 comes from. It's dividing the 1,000,000 gallons by, see, you notice the answer, dry solids is equal to this times that, which is 10,800 pounds per million gallons. It's not per million pounds, it's per million gallons. And the way he got that was dividing the million by 8.34. Or dividing 1 by 8.34, and that'd give you 8.34 per million. And so the 8.34 just comes from converting water weighs 8.34 pounds per gallon. And then he wanted to know the sludge. The sludge has a concentration of 8% and a specific gravity of so much. In this case, the volume is 10,800 pounds per million gallons. It has 8% solids, so divided by 8 and by 0.08, and the specific gravity is 1.03, and you end up with 131,000 gallons per million gallons. Okay. Then the next one, there's a series of these that I suggest that you read, and they talk about chlorine, and it just has some practical things, and I will leave that to you to read. So you can read 1131 on WT6 is results of a chlorine demand test, and it says to draw the curve. The curve is drawn down below, and so it says draw the demand curve. Here's the demand curve. What is the breakpoint chlorine dosage? It looks like it's about 1. break point is there. And C is what is the chlorine demand at a chloride dosage of 1.2. So you come out here at 1.2. Of course, you can actually go up to the table and read it a little better, a little easier. 1.2. The residual chlorine was 0.4, and you added 1.2. So the demand was the difference between 1.2 and 0.4, which is 0.8. Okay? Now, WT 7, 8, and 9 are discussion questions with the answer. And time is running kind of short here, so I think I won't read those to you. You can read those. But it just lists 3 possible methods of controlling crown corrosion in a large concrete sanitary sewer, for example. Crown corrosion in a large concrete sewer can be retarded by ventilation and chlorination to control hydrogen sulfide generation in synthetic coatings and linings. You know, and it's just a series of questions like that. Now, question 1157 and 1158 are kind of nice if you're not familiar with water treatment plants. What they do is they outline a sequence of unit operations and chemical additions and then briefly state the purpose or the function of these things. For example, on number 57, you have mixing and flocculation with the addition of lime, and you have sedimentation, you have recarbonation, you have granular media filtration, and post-chlorination. And they discuss why you would do that. And so 1158 is a similar thing, 1159, 60 through 61, and you can read those. And so that concludes this section on water treatment. We're not through with all the water treatment, just this one entitled WT. And the next section is water filtration. And water filtration, what I've got here is some information that you could use to solve water filtration problems. Normally the sequence is you clean up the water by going through some type of a sedimentation process. You may add chemicals or you may not. If you've got water that's dirty with sand and grit, you might be able to just use primary sedimentation with no chemicals. If you've got a lot of dead leaves and organic compounds in there, you may have to add a chemical and then let it settle. So you might have to go through the flocculation process. But then you have the settling, then you have the filter, and then you follow with some type of a storage. You would store the water. You have to store the water for 2 purposes. One is you have to store the water to finally get it into, get it chlorinated and get it out into the system. And the other thing is you need some clean, unchlorinated water that you can use to backwash the filter. So you have to always follow filtration with storage so that you can store some unchlorinated water. Rapid sand filter, the depth of the filter is 3 feet or more. The depth of the filter bed is 10 feet. The hydraulic head is 1 to 8 feet. The flow rate in the past has varied from 2 to 10 gallons per minute. Now people really want these plants to be as efficient as possible, and what they do is they normally put in some type of a tank so that they can operate the plant at steady flow. In the old days, they didn't build the big tank. They didn't store the water. And so the water treatment plant, the production went up and down in response to demand. But now most water treatment plants operate at a fairly constant rate. In other words, to tomorrow the rate would be very similar to today's rate. Now in the summer the rate will be higher than it is in the winter. But they don't drastically change the flow rate. They make the plant more efficient that way. So it says modern rates go up to about 8 gallons per minute per square foot on the filter, and a reasonable rate is 4 gallons per minute per square foot. That's the maximum design rate, and that would be if you're designing it for steady flow. Most modern plants would be designed for steady flow, and you'd design it for up to about 4 gallons per minute. The total capacity per filter varies from 350 gallons a minute to 3,500 gallons a minute. You want to try to have at least 3 filters so you can meet the maximum demand with 2 filters. In other words, you want a filter reserve, so you can be backwashing a filter or repairing a filter while you're operating. Some more design information. Service to rapid filters. Backwashing. The normal backwashing occurs after 1 to 3 days. You don't want to go months between backwashes because you can get gross in there. So what you want to do is backwash fairly often. If you don't have to backwash because your load is too low, then that's an advantage of having a large number of filters, and you would just shut off some of the filters. So you can keep your backwash rate about 1 to 3 filters. Backwashing occurs when the head loss reaches some design value. Of course, that can be anywhere from 1 to 8 feet, usually a maximum of 8 feet. Backwashing expands the bed by about 50%, so when you design, if they ask you to design a filter, don't forget to have the concrete tank big enough to hold the volume of the sand, plus about 50% more for the expansion of the sand when you backwash it. Or you can backwash all the sand out of the filter. And then you normally backwash for 3 to 5 minutes at 8 to 15 gallons per minute per square foot. So you can calculate the amount of backwash water you need. And then backwashing normally takes 1 to 5% of the total filtered water. Now, if it takes more than that, then what that means is your water is too dirty when it's going onto the filter, and you need to do some upstream treatment of the water to clean it up. This section, water filtration, page 3, is some information about what they call direct filtration. That's where you filter the water without any pre-treatment. Now, you may have a screen there to remove bicycles and things, but there's no real pre-treatment. So direct filtration is filtration without pre-treatment. Direct filtration is feasible in waters less than 40 units of color, turbidity consistently below 5 units, iron and manganese concentrations of less than 3/10 or 500 milligram per liter, and algae counts below 2,000 per milliliter. And direct filtration is normally done at rates, and the books say somewhat lower than normal rates. And most people I talk to say 10 to 25% lower than the normal rates. And 10% for rapid and 25% for slow sand filters. And we've been talking about rapid sand filters. Before I go to the slow sand filter, let's talk about clear wells. I mentioned that after the filter you'd have this clear well. Then storage volume would be equal to 30 to 60% of the daily output with a minimum of 12 hours of maximum daily consumption. And the clear well capacity should meet the demand when the filters are being backwashed. And then slow sand filtration is a pretty much different process than rapid. It's not just a matter of speed. On a slow sand filter, the thickness of sand is 24 inches to 48 inches. You normally have a gravel layer and there's 6 to 12 inches. The flow rate is about 500 gallons per minute per square foot to about 1/10 of a gallon per minute per square foot. It's really slow, and what you depend on is getting a growth of slime on top of that filter. And it's the biological ooze on top of that, what some people call the schmutz deck, that does a lot of filtering. And you don't usually backwash these things. What you do is you clean the filter by removing a few inches of sand. And when you remove too much sand, then you stop and put more sand back on the filter. And the normal head loss is about 2/10 to 4 feet. And then, of course, in your book they talk about pressure filters. And pressure filters where you put the sand in a container and you run it at higher pressure. So you can make a small filter and provide quite a bit of water treatment. And that completes the water filtration. So the next section is called potable water. Now in this exam that you're going to take, you're supposed to work your problems, and what you're supposed to do is carefully state your assumptions. And so sometimes you may have a trouble knowing exactly how to proceed. And I think they understand that. And what you should do then is if you make a decision that you're going to move in one direction or another, then you write down the assumption that you make. Now, if you work the problem correctly with your assumption that you make, But that assumption isn't the best assumption. You're still going to get some credit for the problem. And so you really want to state your assumptions. And what I've done here is I've worked a problem, the same kind of problem is worked in the book, and I made a slightly different assumption. And just to demonstrate that point. But there's a table 710 on page 716 of your textbook, and that is right there. There's, right here on that page, 710. And there's a table 711. And it's 710 shows the annual average water requirements in gallons per capita per day, excluding firefighting. And for residential, they say it's 75 to 130. And then you have commercial and industrial and public and loss and waste. And so they say you're going to use 165 to 270 gallons of water per person per day. And then they have, that's the average. And then they have the demand multipliers for peak periods. And they got the winter, and they got the summer, and they got the maximum daily, and they got the maximum hourly, and they got the early morning, and they got the noon. And the worst one on there, of course, is the maximum hourly. And let's go to a problem. And we'll be referring to those tables. But the problem here, you got a population of 2,500. Calculate the maximum hourly flow for the distribution system. In other words, you're going to design the distribution system for an hourly flow of 2,500 people. And so you got 2,500 people. I picked 165. And I think what you would do there is you'd say, I'm assuming 165 gallons per person per day. You know, the engineer that grades it might think you should have picked 200. But I doubt he's going to get too excited. 165 is a reasonable value. And of course I got cute with you here. 165 gallons per day per person, and there were 2,500 people, and I assume there's one person per people there. So you end up with 412,500 gallons per day. And so then I converted that to gallons per hour. So the average flow rate per hour is 17,187.5 gallons per hour is the average. And then to get then I multiplied by the summer multiplier to get the average flow in the summer, and then I multiplied it times the maximum hourly, which is 3. Your textbook worked a problem just like this, and it didn't put in the summer multiplier. And I think you go either way and put down that you're assuming that the maximum that you would have to. You can either work it the way he did and leave out the summer multiplier, or put it in. But I think you need to write down your assumptions so you can defend what you did. Now then, so you end up then with the maximum hourly flow of 67,000 gallons per hour. I rounded off 67,000. Now you got your fire demand. The fire demand, he gave you an equation in your book where the fire demand is equal to 1020 times the square root of the population in thousands. So the population is 2.5 thousand. So when you plug in P, it's 2.5 because the population is in thousands, times 1 minus 0.01 times the square root of the population again. And so you end up with fire demand of 1,587 gallons per minute. But we want gallons per hour. So you can take the 1,587 gallons per minute times 60 minutes, and you come up with the gallons per hour for fire. And so you can come up then with a maximum, the amount of water that you need for fire, the amount of water that you need for other services. And then in your book, and all books that talk about water systems say you should take into account growth where you can. You should make the plant larger, or the distribution system larger than you're serving today, because these towns have a tendency to grow. And so I took 50% of the total as growth. Your book makes some recommendations dependent on, he talks about large cities and small cities. I assume that 2,500 was a small city. So I took a growth of 50%. And then I ended up with that many gallons per hour. And so that would be the design flow for the distribution system. That would not be the design flow for the water plant, though, because I could design the water plant if I put a big storage tank. I could design the water plant for essentially steady flow, I'd probably use the maximum day in the summer for my design for the water system. Well, let's see what I'd use. I worked that next. I use the maximum daily demand. Why? I'm lucky. I guess when you teach a course more than 20 times, sometimes you remember some of it. All right, so in this case, for the water treatment plant, we need the maximum daily demand. It's the same computation. You can go through that. I'm running out of time, and not for the total course, but time for this water and chemistry. So let's go on to the next section, which is basically, the next section is sedimentation, and I had already written skip on that. This is a nifty way to design a sedimentation tank using laboratory data, and I gave it to you. I doubt that that's going to show up on an exam.
Which set is that?
That's one called SET, Sedimentation-1. So that's for your information. I think you'll really like it if you haven't taken a course, because it shows how to take laboratory data and design your sedimentation tank and come up with the efficiency. But I had already written skip. You can see it right there. I'd already written skip. I didn't plan to cover that. I gave it to you for your information. Now then, this next one is just the material taken from your textbook. And there are a couple of items in here on page 712 of your textbook. There's an example problem, and I just wrote on there, and I'm going to zoom in on that example problem on page 712. And I just wrote on there the manganese, you take or magnesium, I'm sorry, magnesium, you take the molecular weight 24.3, the valence is 2 divided by 2, and that would be the 12 that goes here, and this 20 that goes here is the molecular weight of 40 divided by 2. The 50 is for calcium carbonate. It has a molecular weight of 100. Since you're dealing with calcium, magnesium, valence of 2, use a valence of 2. So what you're doing is converting those to calcium carbonate. I just want to show you where this came from.
Doesn't matter that 24.3 divided by 2, they just kind of round it off.
Yeah, you know, that always bothers me. Now, when I do research, or I'm going to publish the results, I use those numbers and round them off. But when you work at a water treatment plant or a sewage treatment plant, they just round them off. And they would call that 40 divided by 2. And again, this is an outgrowth of training people that a lot of them in the beginning didn't even have high school degrees, and they were training them to do these computations. So they didn't have calculators. They had slide rules and adding machines, and so they did a lot of rounding off, and that carries over, and people are still doing it. This shows that flow chart. This on page 715. That flow chart for doing the alkalinity problems, and it's the same. It's the same thing that the other one is in sentence form. This is a little flow chart. All right. On page 722. There's a plain sedimentation problem, example, well, it's just an example. They don't have a number. But it's example on page 722, and it says assume a velocity and calculate the Reynolds number, and it goes through it. And actually on those you can solve, they say you can use figure 7.6, or you can use equation 739. And that chart is on page 723. What I would do if I was solving this, that chart is, you can't really get very accurate answers off that chart, but you can get approximate answers. So what I would do is I'd get an approximate answer off the chart, and then I would check it with the equation. But at least from the chart, you can tell which equation to use. You got an equation for here, you got an equation for this zone, and you got an equation up here. If you use a graphical solution, you at least know which equation to use, and then use the equation. It's more accurate. And I believe that gets us about as far as I think we need to go on this. As I say, the book is well written. In the back, on page 732 of that chapter, they have some typical, this is page 732, they have some typical municipal systems. They got one for groundwater. They got sequence 1, sequence 2, and sequence 3 for groundwater. I'm teaching a course in public works this semester to some senior civil engineering students, and I talked to them about water treatment, and I asked them to write a little report, just a verbal description of the regulations for the state of Texas pertaining to water treatment plant for a little Boy Scout camp, and it was a groundwater system, and of course they made some mistakes that you'd expect from an undergraduate student. But what they did is sometimes for good clean groundwater, they put in a full-blown water treatment plant that you'd put in for taking water out of the Mississippi River. That would be a common mistake. So this outlines the type of systems that you'd expect to find in various types of water. For example, here it says for lake or surface water that's typically turbid and carrying odor and color. And then river surface water, very turbid. And then on the next page they have for hard water, and then on the following page 730. This is good stuff. On the following page they show where you'd normally add your chemicals and so on, and show a normal order that you'd put these processes. And remember that what you do now, because of the recent changes in the EPA regulations, you'd put your chlorination right down here at the end. You wouldn't put chlorination up here. You'd wait till you removed everything. If you kept up with the EPA regulations, you notice they really cut down on the amount of turbidity and color that you're allowed. And the reason they did that, these things react with chlorine to cause these chloroform. And so you remove all that. Or you quit using chlorine. They decided to tighten up on the things that discolor the water that react with the chlorine, so we could keep on using chlorine. And then on figure 710, it shows the application points for the chemicals, and it names the chemicals. So I think this is pretty good if you're not familiar with water treatment plants. You can see how these things operate. And let's take a, do we normally take a break?
Mm-hmm. Yeah.
We finished the chemistry and we finished the water. We still got sewage and solid waste, and we're on schedule. So if you take a 2-minute break. But I'll assume you're going to take 2 minutes at the end, and let's cheat a little. Why don't you take a 10-minute break? Is that about right?
10 minutes, sounds good.
Yeah.